Wouldn't it be magical to experience the primeval climax forests the first European explorers witnessed in New England? What they found were some of the most beautiful and productive temperate forests they'd ever seen, stretching far inland beyond the horizon. In the 400 years since Europeans colonized New England, its primeval forests were almost entirely cut at least once, much of it cleared for agriculture, cities, and towns. Today, only small patches of its original ancient forest remain, and most of those are not easily accessible. Although much of the previously cleared farmland has returned to forest, less than 1% of original ancient New England forest remains, and that's in a scattered collection of fragments. Relatively few people have seen these remnant old forests, and many who have didn't even recognize they were in old growth, because there are varied expectations about what a truly old New England forest would look like. Some imagine an ancient forest to be composed entirely of spooky, contorted old trees with low, imposing limbs. Others picture them to be enchanted, garden-like mystical forests with huge trees of impressive stature. Still others may expect them to be collections of geriatric trees well beyond their years of good health and productivity, in need of culling to restore forest health and vigor. There are various definitions of the term old growth that vary with the amount of and the length of time since the last human impact on the land. In any case, a forest left undisturbed long enough develops certain recognizable qualities. Old eastern forests can be enchanting places. They can have large and gnarly old trees. And some do have a mystical, beckoning appeal. They may be a mixture of all these qualities. They can have a much more diverse understory. And they certainly are not unhealthy or in need of our intervention. The primeval forests had attained their maximum natural potential after thousands of years of development and adaptation. What man has done to them since has only degraded them to one degree or another. Primeval forest provided everything needed to sustain life for native people adapted to its ways. It provided food to eat, shelter, healthy air to breathe, pure water to drink. European settlers came from places that had long ago greatly overexploited their forests. To them, this wild forest was limitless. They did not recognize then that the forest gave and sustained life on Earth, so its resources were quickly consumed and largely exhausted. So exactly what are some of the characteristics of eastern old-growth forests? By far, most of New England's forests are young, up to perhaps 150 years old or so. Structures such as stone walls indicate this land had been cleared for agricultural use. Young forest on recently abandoned open land is clearly recognizable with its typically dense growth. As it grows a little older, weaker trees die off and the woods thin out. All the trees are virtually the same age and still have thin branches at sharply vertical angles to the trunk. Those vertically angled joints are very weak and will easily break apart, whereas more horizontal branches will survive. Wind and ice storms mercilessly take their toll on the weak. This natural pruning when branches are smaller and weaker leaves the strongest ones to continue the tree's future growth. The tree can easily seal off these small wounds quickly, usually before any fungus can invade the tree. Some will perish, thinning out the densely packed stand. But nothing here is waste. Everything is recycled to build and maintain the forest. If there are some larger diameter trees, they're not necessarily old, just well nourished. As the forest begins to mature, diversity of sizes and ages becomes evident. At about 120 years or so, it's just entering its adulthood, and beginning to take on older forest characteristics. Soil and duff layers are slowly rebuilding. Understory plant and beneficial soil fungus communities are becoming better established. It may take centuries to recover from land use practices of the past, but some of our forests currently already have a century or more of development on their return to old growth, and they'll continue to adapt to their environment. The elders in an old-growth forest have lost those weak limbs. They sport a crown of just a few large, nearly horizontal limbs. That wispy, twiggy growth is a thing of the past. Without the bushy tops of thin, fine twigs that intermingle with those of their neighbors, their stag-headed structure makes them stand out as individuals in the canopy. Younger conifers, such as this hemlock, have branches 1 to 2 inches or so thick. An old hemlock will have fewer and thicker branches, up to perhaps 5 or maybe 6 inches thick. When you see a hemlock in the northeast with branches 4 inches or more in diameter high up on the trunk, you're looking at an older tree. But in a forest, a large tree with thick spreading limbs well below the canopy is not a tree that grew up in the forest. This indicates it grew in open conditions, such as a pasture, where there was little or no competition for light, and eventually a forest grew up around it. So this kind of tree is not an indicator of a particularly old forest. Trunk sinuosity is another characteristic often seen in old forests. Over the years, a tree's growth may be biased in the direction of light availability, and that direction may change over time. As a result, the trunk may become curved and serpentine. The bark of many tree species changes dramatically with age, some more so than others. In general, young trees have thin, smooth bark which, with a bit of age, becomes cracked and split into plates. Some develop very thick bark ridges with deep furrows. Eventually, outer layers may slough off, resulting in a smoother surface again, known as balding bark. The oldest bark is at the base of the trunk, so the older the tree is, the farther up the trunk the older bark characteristics will appear. A northern red oak at about 100 years old. Bark ridges are still flattened. This one is about 180 years old. Bark ridges are thicker now. It has some balding at the base of the trunk. And this is one of the oldest known northern red oaks on Earth, now about 350 years old. Characteristics of its old bark are seen all the way up the trunk, and it's balding at the base. Young black birches have smooth bark that will change markedly with age. Old trees are not necessarily large trees, and large diameter trees are often mistakenly thought to be much older than they are. Eastern hemlocks have thin, scaly bark when young. As they age, the bark develops into thicker plates and ridges. Hemlocks hundreds of years old often take on a cinnamon red color. This is a sizable tree, but hemlocks can grow extremely slowly when shaded. A core taken from this hemlock was accurately ring counted to 293 years at 3.5 feet above the ground, so it was 300 or more years old. It was only 25 inches in diameter. This small, dead hemlock stump was about 85 years old. Trunks of fast-growing, younger trees taper in diameter toward the top. Old forest trees add girth in their upper trunks, which reduces taper, and they become more columnar. These characteristics of old trees, canopy structure, bark patterns, columnar trunks, develop over centuries of time and are visual clues to the age of a forest. Species such as hemlock and blackgum can easily live to over 500 years. Many others reach well over 400 years. With time, the shade-intolerant, early successional tree species of our northern forests are shaded out by species such as sugar maple, beech, and hemlock, whose offspring can tolerate the shade of their parents, and the canopy becomes dominated by such climax species. This is the normal, natural succession path of a northern hardwood temperate forest. Trees will get toppled or broken off by wind. This opens up random gaps in the closed canopy. In an old-growth forest, gaps are typically small because large, old tree roots are often grafted to each other into a massive anchoring network. Gaps can also result from insect, disease, or ice storm damage. Sunlight can now reach the forest floor, stimulating growth of new trees. Over time, the forest becomes a mixture of tree ages, some old, some middle-aged, some young, some dying or dead, others just beginning life. When trees are uprooted, they pull up a mass of roots and soil. As the roots rot away, the soil settles into a mound. A hole or pit is left behind. The warmer, drier, exposed mineral soil of the mound, free of humus, is a perfect site for the tiny seeds of trees like birches to germinate and grow. The pits can be wetter and cooler microhabitats that do accumulate organic matter and may hold water for forest creatures. This pit and mound, or pillow and cradle, topography is characteristic of old forests that have never been cleared and plowed for agricultural use. The forest floor accumulates fallen limbs and logs, coarse woody material that slowly decomposes and holds a tremendous amount of water and carbon. Soil that has been building for thousands of years supports a rich community of understory plant life, with both common and no longer common species. Undisturbed old-growth forests typically have a far richer mix of fungi and lichens, and plants such as mosses, liverworts, ferns, and many others that have evolved to thrive in the moist, intact forest floor duff layer. The result is a much more complex and varied understory. Several plants can be particularly good indicators of old forests in New England. Hobblebush, a viburnum, is frequently found in old forests. It often forms dense thickets. Canada yew, a low-growing shrub, is less commonly encountered. Wall scalewort is a liverwort found mostly on trunks of old, late successional trees, such as sugar maple and beech. Shingle moss on tree trunks is another good indicator of old growth. An abundance of intermediate wood fern may suggest an older forest. One of the best old-growth indicators is lungwort. This lichen can't tolerate polluted sites, but thrives in clean, humid, undisturbed old forests. What is the value of woody debris lying around on the forest floor? Well, for one thing, it can be a barrier protecting many plants and tree seedlings from browsing herbivores. It provides structural complexity, creating microhabitats needed by large numbers of plant, fungus, and animal organisms. In winter, small mammals find safe refuge from predators in runways, around and under logs. Bears often spend winters in brush piles. Logs help prevent erosion on slopes. Once fallen, hemlock and pine become carpeted in moss. Large logs remain soggy sponges until they're completely rotted away. That will be many decades, during which they'll be homes for generations of organisms. Wet, moss-covered logs are ideal nurseries for birch seeds to sprout and root. Even if they don't become nurse logs, they provide critical, moist habitat, loaded with small life forms, the basis of the forest food chain.
When I walk through the woods, I love looking at the trees, but I especially like looking at the old dead trees that are lying on the ground. That is an important part of a tree's life cycle and vital to the forest soil. Quite often, the most important things in the forest are the things that we're stepping over, like this dead log. It's soft and spongy, it's holding water, which is a wonderful place for the moss to grow. I see tiny mushrooms that are growing and a small hemlock seedling. This log is much further along in its state of decomposition. It is being eaten by a fungus that attacks the lignin and leaves behind the cellulose. And you can tell by just feeling it, it's spongy and holds water. This is important for a lot of the little creatures like amphibians that like to live under these logs. You can also see the fungus that's in the log eating it up. Often you'll find bears and raccoons will dig through these logs to try to find the insects that are eating the wood. So this log has been on the ground for about 25 years. It is being eaten by brown rot fungus. The brown rot fungus eats the cellulose in the tree and leaves behind the lignin. It has a different appearance. It's very blocky and chunky, and you can break it apart and you can see the insect tunnels that have gone through the wood. And it has this wonderful distinctive reddish color. This decomposition adds a great deal of carbon to the soil. How a tree dies will affect its usefulness to wildlife. If a tree loses a limb, fungus can get into the heartwood of the tree and create hollow cavities where wildlife can nest. So we're standing beside a wonderful old tree here. As this tree reaches the end of its life, it will start to decompose, limbs will start to fall off. As the limbs fall off, then it becomes an opportunity for fungus to get into the tree and rot out the heartwood. As it rots out the heartwood, you get hollow cavities in the tree. Quite often we think to create an old snag or wildlife tree, common practice is to girdle it. But when the tree is girdled, it gets into the soft sapwood. The sapwood rots in a different way from the heartwood. The wildlife that use the old trees want to use the heartwood. So girdling a tree will not necessarily create those habitats that we were looking for in the woods. So we need more hollow trees in our woods, and the larger the tree, the larger the hollow, the more wildlife can use it. Most of our trees in our young forest have small holes that a lot of birds can use, but the larger mammals cannot use them. And large hollow trees can also be used by things like turkey vultures and black vultures for nesting. They need a big tree. It's hard to find hollow logs in the forest. Often when a tree falls down, if it's been knocked down by a storm, it wasn't hollowed out to begin with, and the log will rot from the outside, and it's not very useful for the wildlife. It will eventually rot back into the soil. It will become a home for salamanders underneath the log. It will become food for lots of creatures that use these old logs, but it's the hollow logs that are the high rent real estate in the forest. So there's a new exciting field called morticulture. It was started by a professor, Mark Harmon, at the Oregon State University. They call him Dr. Death. 30 years ago, he chopped down trees and he's watching them rot. He says it's part of a 200-year-old study to see how trees return to the soil. And it's a fascinating idea to see what happens to the trees after they die and while they're dying. So what he's been finding is that the older trees have more biological diversity, they have more fungi, more interesting life forms living on them, and when the trees fall down and rot, They are far more biologically diverse than the living trees. As the trees age, they become increasingly more diverse in the species of fungi that are associated with them, and they harbor a whole lot of life. Often when we go for a walk in the woods, we are interested in looking at the trees. We often don't look down on the ground. And that's where really the forests begin. That's where the seeds germinate, and without the soil, we wouldn't have the trees. When a tree rots, it adds its organic matter back to the soil. When we harvest an area of the trees and do not return the carbon back down to the soil, it depletes the carbon that's in the soil. It's important for old trees to fall over, continue their life cycle of decay, and return to the soil. That will keep the soil healthy. With repeated logging of our forests, the use of equipment to go in and harvest the trees, there is a compaction of the soil that's done by the logging machinery. That takes a long time for that soil to recover. We've all seen old logging roads and nothing's growing on them. The forest floor is the protection for the tree roots. Anything we do that damages the forest floor hurts the trees. So whether it's logging equipment or ATVs, any of those things have the potential to disrupt that forest floor and the creatures that live there. We don't know how many times we can harvest our forests and maintain the health of our soils. So next time you take a walk in the forest on a trail, notice how hard the ground is. And then go off the trail into the woods. If it's a nice healthy forest, you should be able to feel your shoes as though they're walking on pillows. A healthy forest soil should be light and fluffy and spongy.
Northeastern forests are being affected by various things: invasive insects and plants, invasive earthworms, tree diseases, warming climate, and so on. So, do all of our forest lands now require active management to thrive, or even to survive?
One of the remarkable things about forests is that they are completely self-sustaining. They develop into complex, resilient, and thriving ecosystems without human help, and regardless of the type of natural disturbance regimes that they're exposed to along the way. One of the things that we often hear these days is that our forests need to be actively managed in order to improve their resilience and their health in the face of increasing disturbances related to climate change. But the capacity for resilience is largely a function of the complex arrangements and diversity of trees in a forest, both of which tend to increase over time in forests that are protected from management as compared to forests that are exposed to active management. So our forests are actually better off in most cases when they are left alone to develop structure, diversity, and carbon storage than when we go in and try to manipulate them. Ironically, forests develop complexity in no small part from being exposed to the very disturbances that we aim to make our forests more resilient to. So the insect outbreaks, the diseases, the windstorms. These natural disturbances kill individual trees or groups of trees, which results in gaps in the canopy, irregular spacing of trees in the forest, a greater variation of tree sizes and heights, and a greater number of large dead-standing trees and down logs on the forest floor, all of which enhance the structural complexity of the forest. And dead-standing trees and down logs are not symptoms of a sick or unhealthy forest. These are critical structures that provide habitat for a wide variety of animals, nutrients that enrich the soil, and growing space that allow for young trees to regenerate in the gaps created by the dead trees. And large trees like the one I'm standing next to here are very important structures in a forest, both in terms of carbon storage as well as habitat value. And our research has found that large live and dead trees are about 2 and 4 times more abundant in protected wild forest as compared to forests that are exposed to active management. And forest structural complexity has been shown to be a strong predictor of biodiversity in a forest because of the increased habitat niches and resources that are made available in structurally complex forests.
But older, unmanaged forests have value that extends beyond their natural resilience, complexity, soil health, and habitat value. It's now becoming clear that natural, time-tested forests can significantly regulate our weather patterns. Photosynthesis draws in carbon dioxide and releases large amounts of water vapor. Leaves evaporate and transpire the water. Vapor accumulates and rises with the sun's heat. When the water vapor encounters cool air, it condenses, forming clouds. If conditions are right, we get precipitation. Atmospheric physicist Anastasia Makarieva is the co-developer of the biotic pump theory, which explains the crucial importance of the role that old-growth forests play in the Earth's hydrologic cycle.
So how plants get their water? Moist air must come from the ocean to land, and then it rises, and then as the air rises it cools and water vapor condenses and precipitates. So this is how plants are watered. And so the biotic pump explains how this process is in fact regulated by forests themselves. The air moves governed by pressure gradients. What is a pressure gradient? It is when somewhere there is less air than somewhere else. Then the air streams to the area of low pressure. If the air is moist, and it means that it contains a lot of water vapor, and if there is condensation of water vapor, so the water vapor molecules condense into droplets and occupy much less space than before, then we have kind of a rarefication of local air and a drop of pressure. And this process generates a pressure gradient that can drive winds. So by regulating the rate of condensation, forests can actually regulate the wind. And how do forests regulate the rate of condensation? So with these green leaves, they have stomata, small openings, and when there is photosynthesis, the stomata open to catch CO2 molecule. But during the same time, there are many water vapor molecules emitted into the air, and this process moistens the atmosphere. And when the atmosphere becomes moist, the probability of condensation and of the ascending air motion rises exponentially with the amount of moisture. So by regulating the rate of evapotranspiration, forests can actually induce the ascending air motion, and when there is ascending air motion, there will be also a horizontal inflow of air. And it can lead to the moisture import from the water bodies like the ocean or a big lake, and so the forest will be supplying itself with water. The problem is that the water store on land is very transient. So if we stop the import of moisture via the atmosphere, all the rivers would steal all the fresh water from the continents in just a few years. So there must be a continuous process returning water to land. Natural forests and mature forests are especially important because they kind of know and evolved to know when and how to transpire to trigger the right inflow of moisture. Because imagine you have some randomly planted vegetation or an even age stand which just transpires whatever they have in soil. Then, if the atmosphere is too dry and the transpired moisture cannot trigger the condensation, it can all be lost and blown away from the area without triggering any inflow of moisture. So the forest must get more moisture that it has transpired to also compensate for the losses to the stream flow. And if condensation is not triggered in sufficient amounts, then there will be drying of the forest. And this is what happens when we have unnatural stands or tree stands that do not have this capacity to regulate the water cycle in comparison to natural systems that have evolved this capacity tuned to the local geophysical conditions. So when we have large contiguous forest, it brings moisture even further inland. For example, if we speak about New England forests, we can say that the process of succession that began 100 and 150 years ago is transforming these forests to a state when they are more and more competent buffering the extremes, both droughts and extreme winds and floods. So as succession goes and we allow it to continue to transform these forests into their natural state, we can expect a better and better regulated and stable regional water cycle. One thing that is important in the biotic pump mechanism is that the forest moisture store is an extremely valuable capital or treasure of the forest, which shouldn't be wasted. It should be used wisely. And so when there is a logging in the forest which opens the canopy, this leads to huge losses of soil moisture. Why? When there is closed canopy, the canopy is warmer than the soil. And because of the soil, air above the soil is colder, it doesn't readily go up. And so the soil is moist and the trees transpire from the underground layers. So we have moist ground surface in the soil and the fire probability is low. Now, when we cut the trees and open the canopy, the ground heats directly by the sun, is heated, and then there is a much stronger convection which just brings moisture away. The soil dries up, the upper layer, and so the temperatures can rise up to like 50 degrees centigrade and the flammability increases abruptly. So actually fires follow logging. There was a study made in Russian so-called intact forest landscapes, which are landscapes where you cannot see any human disturbance when you use satellite images. So during the last like 50 or 30 years, depending on the images that you use. And they found that in intact forests, the number of fires is 10 times less than in the forests that are exploited and logged and so not intact. So this is very important. The planet does warm, so there can be warm and dry periods, but still, if the forest is intact, it can withstand it because it has powerful mechanisms of how to stabilize its moisture store. But if we add to the global warming also disturbance by logging, we just undermine the forest's capacity to manage droughts, which it does have. There is a natural fire dynamics in a forest, which is like relatively infrequent fires, but then you add logging and the tree stands become even-aged and young, and they have much higher flammability, and at a certain point the threshold is like passed and the ecosystem is put on the self-degradation trajectory and the landscape is trapped into a drier, depauperate state. So when we hear about the Canadian fires, huge carbon emissions from these fires, this is packaged as global warming message. But in reality, if we look at the Canadian forests, they are logged at a rate of about 1% per year, which means actually that in the steady state that the mean age of these forests is 50 years. So these are not natural forests, but basically intensely exploited forests. And this dramatically reduces their capacity to regulate the water cycle and to keep moist. Just because the climate regulating capacity cannot be maximized simultaneously with the commercial value of timber. These are different things. The commercial tree stands is what we grow like a tree garden or something and just consume for our human needs. And we need to decide how much natural forest we need for climate stabilization and how much land we can allocate for these commercial and economic needs. These are separate categories. We shouldn't mix them up pretending that any forest can do this climate regulating job. This is not so. Forests can only function normally and most efficiently in terms of climate regulation when they have the structure to be stable and to perpetuate in time together with their climate. When we arbitrarily change what is in the forest, we decouple these mechanisms and forest's ability to stabilize environmental and climatic conditions deteriorates. So we need to keep these natural forests on sufficiently large territories for them to continue regulating our climate for us. So there is a red line which we cannot cross if we don't want our climate to destabilize to a state which will prohibit our normal existence.
So we all need and use wood products, and it's revealing that the most progressive form of forestry, so-called ecological forestry, attempts to mimic the structures that develop naturally in unmanaged forests over time. In other words, ecological forestry uses nature as a model to retain some elements of diversity and structure while obtaining wood products. So unless we are managing specifically for wood products, there's no particular need to manage forest trees. We just need to protect them and let them do their job, which they do incredibly effectively all by themselves.
After thousands of years of evolution, primeval forests were as well adapted to conditions and as resilient as they would ever be. Their genetics were fine-tuned over the millennia. When these forests were cleared, much of that genetic stock and the adaptability it provided was lost. Many species don't recover well after old forests are logged, and we don't even know how many have disappeared forever. With such a large percentage of eastern forest having been cleared, genetic diversity is greatly reduced. That is not a good thing for our future. Dramatic landscape, but it doesn't support much life. A beautiful vista, but minimal habitat for humans. No landscape provides more of our needs than natural, time-proven forest. Much of the planet that was once green forest no longer is, but extensive tracts of nature-managed green forest are vital to our very existence. We've recognized how important a few of the more charismatic American species are that we nearly eliminated. Others haven't fared as well. We're finally now discovering just how critical it is to bring back the most essential of all, the primeval forest conditions that have given life to us all. There is great concern about what the extraction of forest resources is doing to the planet we live on. It seems only reasonable and wise that we should not exploit all forest land. Rather, much of it should be revered as life-sustaining. As the late ecologist Chris Kane said about large old-growth trees, it's not just about the three-dimensional, it's about the fourth dimension, time. Woodlands cannot attain old-growth conditions by our manipulation. Natural biological conditions cannot be mimicked or hurried. They must play out over time. The forests of New England are undergoing the most successful recovery in history, the older ones just now beginning their return to old-growth conditions. There is a call to permanently set aside a significant portion of our New England forest lands as forever natural and wild. And it's easy. We only have to leave it alone.